Let's talk about DC motors. The basic concept behind the DC motor is that if you have a conductor and you have a current flowing through it and there's a magnetic field, you get a force at the right angle. Oops. All right, R for right, F for force. Conversely, the other thing that happens in the motors, if you have a conductor and it is moving with some velocity and there's a magnetic field, you are going to generate a voltage or current through that wire. Okay, so as we do these motors, we'll find that current and motion and things all interact. But let's take just a second to go back to the original electric motor. It was designed or invented by Michael Faraday in the, well, it must have been the 1700s. Don't quote me on that, though. I don't have it written down. Basically, if you have a piece of wire hanging from a hook and you connect that to some voltage source, we'll say that's plus, doesn't matter, and you have a magnet here, we'll draw as a bar magnet because that's what he used with, we'll call that north and that south, and you get the magnetic field going like this, okay? And what Faraday did was he filled this up with mercury up to some point, and he connected that mercury, because it's conductive, to the other end of his battery. And now I have a current flowing through this wire, and I have a magnetic field crossing it, essentially horizontally here at the end of the magnet. So it's going to create a force either coming out of or going into the screen here, depending on which way the current flows and which way the magnet is. And so essentially this little wire dangling around would kind of circle around and around the magnet. And that was the first electric motor. So let's move on. Mid-19th century, so that would have been the 1800s. Okay. Simple operation. When you're dealing with DC motors, you crank up the voltage, you get more speed. Reverse voltage, reverse direction, that's for permanent magnet motors. Okay, we've got to be careful here. Introduction of AC power in the early 20th century. We've replaced a lot of DC motors with AC motors because they're basically simpler and cheaper since you don't have to do brushes and switching. But DC motors are very nice to control for speed and torque. Particularly speed. A lot of the AC motors, particularly induction motors, are almost impossible to control for speed. So DC motors are nicely controllable. We still use them a lot. And they're handy for portable applications where you're running off of a battery too. Basically, two modes of operation. We can try to control the voltage across the device, which has a strong impact on the final velocity, or we can try to control current, which directly controls torque. But basically, because the way the motor works is the torque is generated as a function of that current, because the current carrying conductor introduces electromagnetic force acting along on the conductor, like we mentioned at the first slide. And since that conductor is moving through a electric or magnetic field, you get an electric potential generated across that conductor, which is your back EMF, which we'll get to that. So here's an example of a small permanent magnet brushed DC motor. The shaft here is connected to the rotor, or the rotating part. This is the stator. We have connectors here to let the electricity in and out. You can't see the brushes. This has brushes. They're basically dirt cheap. These examples are not very powerful either, but they work. You can run them off of batteries. So let's go through the terminology. Rotor is the rotating part. What a surprise. That would be this area here, the part of the motor that's connected to the output shaft that rotates. And it's in yellow, okay. Stator is the stationary part, which is in green here, okay. The field system is the part of the motor that provides the magnetic flux. Now, the field can be provided by a permanent magnet, or it can be applied by windings or electromagnet. And we'll see some examples of both, depending on what you're doing. They're both fairly common. The armature is the part of the motor which carries the current that interacts with the magnetic flux to produce torque. So the field system could have been current carrying, or it could have been a permanent magnet. The armature is the other piece that basically is interacting to generate torque with obviously with a permanent magnet motor. That would be this part here. With a wound motor, it's typically this part. Now, there are brushless motors where the magnet is on the rotor and the windings are on the stator, but this is, but we'll get to that too. And brushes in a brushed DC motor is part of the electrical circuit through which a current is supplied to the armature. So I've got current coming in from the outside world, okay, and I've got this rotating windings here on the rotor or the armature. I have to get current from the stationary world to the rotating world, so I have these brushes of carbon compounds and brass and different metals that rub on the final piece, the commutator, which is in contact with the brushes and makes that connection between the rotating and stationary world. And the commutator also does switching, as we'll see in just a couple slides. This here's a picture of a rotor. This is a cheap DC motor with just 3 poles. That's about as cheap as they get. So this whole thing rotates. Here's the windings. The commutator is here. Different kinds of windings. Basically, the previous example, the number of parallel current paths equals the number of poles. So it's good for high current, low voltage motors because you've got everything turned on at once. Wave winding, there's a couple current paths, and you get these complicated winding patterns. And if you want to stop the tape and trace through them, you can. But I don't know if it's that important at this point. The stator, in this example, this is the stationary part of a permanent magnet DC motor, and these are the magnets here and here. Brushes, here's examples of brushes. Basically, there's a spring in here somewhere, and you can see it in that picture of that brush that holds this conductor part against the commutator. And you can see this is in different sections. So depending upon the position of the motor, we're changing how the current flows through all those windings because we're contacting different pieces of that stator. Let me go back a couple pictures. So we'll be injecting current into, say, here, and that changes how the current flows through all those windings, and we'll get to the details. Commutation basically provides a lot of mechanical switching. It changes the direction of the current flow through particular coils, or it takes current out of one coil and applies it to a different coil. And it's just a mechanical thing. You have all these strips of brass with the little spaces in between, and the wires, all these windings are connected to all these individual commutator strips. Commutator and brushes. So again, here's a low-cost brush assembly. It rubs on the commutator there, and this commutator looks like it has 1, 2, 3, 4, 5 segments to it. So any 2 of those are going to be energized at any given time. But let's talk about all that switching and all that fun stuff and why we have to do it. Again, we have torque generation needs 2 elements. We need a current, and we need a magnetic field. Okay? And when you have a current and a magnetic field, you generate a force on that conductor when the current starts flowing. And our equation here is right there at the bottom. And I guess I didn't really need to write that out, did I? So I have a current, I have a flux density, and I generate a force in this direction. So basically what we can do is integrate that force over the entire length. So if I integrate along here and along here, and these are the elements of the coil that are essentially perpendicular to our magnetic field, which is operating in this direction. So I can integrate over the lengths of the coils here, and I get, well, my equation for force, dF is the current times dL, the length times the magnetic flux density, and my final force is the current times the length times B, and my total torque generated, since I have wire here, I have wire here, torque is obviously the force times the distance, the radius. Well, I have a force here, and I'm drawing it the wrong way. And I have a force there, and there's 2 of these, one on each side, and they're basically this distance r from the center. So 2 times F times R. Substituting in, I get a equation here for the torque of a coil. And if I have a number of coils in the motor, and each coil set is wound round and round and around, several times, the total torque generated from the N coils is the number of coils times 2 times the current times the magnetic field, the length, and the radius from the center, okay? And I can rewrite that as all these terms times the current. So these terms here under this, over this bracket, are constants for a given motor. So we can redefine that whole mess as K torque, okay? And we can find that constant experimentally if we can measure torque by just holding the motor at a 0 speed, applying a voltage, measuring the current, measuring the torque, and we can calculate that constant. So the torque, because the torque is, by substituting back in, torque of the motor is that constant times the current. Now, obviously you want a large current or large torque at any given time, right? But there's a lot of physical limits. Large torque constant suggests you want large number of turns, very long length, very large radius. That's basically physically the size of the device, how long, how big, right? And a large magnetic flux, getting that, it depends on how you're generating the flux. We can either use permanent magnets, and to get a larger flux, we need to use more exotic magnetic material, or we can use an electromagnet, and then that flux becomes a function of the winding style and the current flowing through it. The other piece that we mentioned in the first slide is when that conductor is moving in a magnetic field, which it is if the motor is spinning, we generate a force, the EmF, or derivative of the electromotive force, or voltage, is the velocity times the actually it's a cross product here because we're talking vectors, the magnetic field times the dl, or length. So if we integrate over the entire length, our electromotive force is the velocity times that magnetic field times the length. So if this is my force, or my speed moving in this direction, my magnetic field is that direction, I get the current flowing along the wire. And of course, the reason for the cross product is these are vector quantities, and having everything at right angles gives us the maximum current. And for our given motor design, since we have a number of armature coils are in series all wound around, we get the total back EMF, or electromotive force or voltage, is equal to times the number of turns times the radius times omega. That essentially radius omega gives us our velocity times the magnetic field strength times the length of that coil. And we can get that all out here. And again, you see this is a series of numbers that are constant for any given motor design, and that leads us to a constant here where we say that the back EMF constant is equal to all these terms here times, in the units are obviously volts per radian per second. And so that back EMF is generated due to the rotation of the motor armature, and it opposes the applied voltage and is proportional to the angular speed omega of the motor. Okay, so as the motor accelerates, this back EMF increases, and it opposes the applied voltage. And in theory, if it would reach some point where, as these two voltages are opposed, your current drops because your voltage across the windings drops effectively, and at some point you would get a steady state final speed where the current is equal to zero, and the speed is constant, and the voltage, the EMF, is going to equal your applied voltage, but of course there's always friction, so you never get to that zero current. So that's the basic concept, and there's a lot of variations. We talked about you can have a permanent magnet motor where this is just a permanent magnet north and south, okay? And the permanent magnet is bidirectional because if I change the direction of the current flowing through these wires in the rotor, I'm essentially going to change the direction of the force, and by changing my external current, I change the direction of the motor, okay? I can do field coil-induced magnetic fields where I have a wound field like we have illustrating here. Essentially, it's an electromagnet, okay? And I can wind that field in several different ways, arrange how the field and the armature are connected in several different ways. The simplest way is a series wound DC motor where here's my voltage in, current flows through the field, through the armature, and back out. So my field current and my armature current are always equal to zero. This is unidirectional because if this is plus and this is minus, I get current flowing this way. If I switch that, minus and plus, I get current flowing the other direction. So that changes the direction of the magnetic field generated by the armature, but it also changes the direction of the magnetic field in my stationary field windings. So the motor torque and rotation generation still goes the same direction no matter which way I do that, okay? Here, if I can wire them in parallel, I have the same voltage across the armature as I have across the field, but I have different currents. Again, this is unidirectional because changing the voltage, changing my source voltage direction changes both magnetic fields. And, you know, this one gives us good speed regulation, doesn't have much starting torque or no load speed. Series wound, you get high starting torque, a high no load speed. And you can actually combine them where you have part of the field wound in parallel, part of the field wound in series with the armature, and you can play these games to get the characteristics that you want out of this motor. Or you can have a DC motor where the field is completely separate and excited separately. That's fairly uncommon. So to get this all to work, okay, we've talked about the commutator, we've talked about things. If I applied if I have my winding here, I'm going to try and draw this. And my current is flowing in this direction, okay? And my magnetic field is running through here. And I get a magnetic force, we'll just draw it as going up that way, right? When I turn 180 degrees, now my magnetic, because I've turned this whole thing around, if the current, you know, from A to B, right, once it's rotated 180 degrees, this is now B and A, and my current goes this way, and my force is now going to be this way, and it's just going to go back to the way it came. So obviously we have to change the direction of the current flow in this winding as it goes past the permanent magnets to make this work. And that's done with this commutator here. So in this case, I have current flowing this direction through this winding, this direction through that winding. It gives me a force here, a force there, okay? And as it rotates, at some point I get to this point and there's no current flowing at all, and actually the way this looks like a dead short, but that's, you don't normally do two-pole motors like this, so that doesn't happen really much in practice. And as it rotates, well, okay, so we've got this is the green coil on the right, and the current's flowing top to bottom, okay? I'll call this A and this B. This is A and this is B. And now we've switched, so this is A and this is B. Now the current originally was flowing this way through this coil, but now that I've switched in this commutator, it's now flowing this way, so my force is down instead of up like it was before. Okay, so I've switched the current, I've switched the direction of force, so now it's going to keep rotating in the same direction, which it wouldn't have if I hadn't switched. And we end up with the same picture here, except we've now reversed A and B. And it just keeps on going like this. So the commutator is essentially doing mechanical switching. So it's switching the direction of the current flowing through these coils as it rotates. So relative to the coils themselves, the current keeps switching directions. But relative to the magnetic field, the current is always flowing the same direction. Here I've got current flowing down, so I've got a force up, force down, okay? If I went back 4 pictures, here we have current flowing down. So we get this relative to the magnetic field, the currents are always flowing in the same direction. Relative to the armature itself, they're flowing and switching in different directions. That single-phase 2-pole, we had problems right where they overlap. I mentioned that. We don't normally build them that way. There's usually multiple things, and so you get just the coils that are closest to the magnetic field being perpendicular to the magnetic field get energized at any time, and we have lots of connectors on our commutator. typical cheap permanent magnet DC motor, the low cost would have just the 3 windings. That was the example we saw quite a bit ago with 2 poles. And that way you don't get stuck at top dead center and you don't get those short circuit problems. But there's still issues with brushed DC motors. The brushes generate electrical noise, they wear out, there's only so much voltage you can put across that sliding contact. Motors in general, heat is an issue, which comes from electrical losses in the windings. They have a resistance. You get eddy currents in the metal parts as they're spinning in this magnetic field. That mechanical structure. Let me go back to the pictures. No, it's probably a bad idea. I did it too late. I did it. Okay. So this material here, these metal windings, support the coils, and they give us a, they enhance the magnetic field, but they're also conductors. And you spin those conductors in the magnetic field, you generate currents, and currents flowing through those laminations are just lost, eddy currents, and it's a loss in power, and it's a parasitic loss, and it results in heat. You get some hysteresis in the magnetic field, you have friction, you have brush contact resistance. There's a lot of things going on that generate heat. Now, brushes are an issue. Another option to go to instead of using brushes and mechanical switching is to go to brushless motors. But without the brushes doing the switching for you, you need to have some kind of position detection and some external switching. So position detecting could be some kind of rotary encoder or a Hall effect thing, or it can be done by measuring the current in unpowered windings and look at the effects of the back EMF to tell you when a particular winding is getting close to one of the poles. And with hobby motors found commonly in radio-controlled aircraft and stuff, the brushless motors, that's how they do that. And they have some type of external switching device which controls the direction of the current through the various windings. This costs more, okay, but it avoids these problems, and they also tend to be more efficient. So if we look at the fundamental relationships in all of the various equations here, you see that our torque is some constant times the current. Our back EMF, this voltage generated that way, is some constant times the speed. In SI units, those numbers are going to be the same. Okay? And we have some resistance in that winding due to the resistance of the wires. We have inductance here in the windings. It's a coil. Obviously, on the mechanical side, given some torque, we have inertia, and that we'll have a load torque here, and it will have some angle and some velocity coming out of that motor. So we can take all of the equations here and the equations for resistors, inductors, and our mechanical side from Newton's laws and come up with a mathematical model given those equations. Okay? So given that, we can treat the motor as a box that is lossless and stores no energy, from an ideal control situation. There are power losses due to the internal resistance and friction and things like that. But the idea here is we supply some voltage and current in, and we get a speed and torque out. So at a steady state operation, why? Because you don't have to deal with inertia and the effects of acceleration. Right? The power flow on the mechanical and electrical sides of the motor have to match. Okay? And our electrical power is voltage times current. Mechanical power is torque times omega. We know that the torque is a function of current, right? And also the voltage is affected by the back EMF, which is a function of omega. So we got some feed-forward feedback terms here that we would put in our total motor model. During constant speed operation, the input voltage is equal to the back EMF generated by the motor. Well, that's, we should say, no load. Right, as soon as you load it, you slow the motor down. But so we have we have our feedback mechanism. Torque is this constant times the current, and the voltage is that constant times omega. Okay, so when the input voltage is equal to the back EMF, our current actually goes to 0. The ideal case, no load, and we're at this no load speed limited thing. So, but even with a load, as the motor slows down, my back EMF goes down, right? And as the back EMF goes down, my current can go up, so there is a fair amount of self-regulation in the speed. So does the load on the mechanical side affect steady state speed? It doesn't affect the no-load speed, obviously, but it does affect the operating speed at any point in time. So here's our motor with the equations, the voltage input through Kirchhoff's voltage law. We have the current times the resistance is our voltage drop across the resistor, our back EMF, and the voltage drop across the inductor due to a change in current. At steady state, this term drops out, makes life simple. So we can say our voltage in is the current times the resistance plus back EMF. And so we can say that the torque of the motor, because torque is the function of that torque constant, is a function of current. Torque equals the IA times KT, and we can substitute that in here, and we get, so our voltage in gives us a motor torque. The resistance over that torque constant is substituting in there times the back EMF times omega, and we can juggle that all around. So at any steady state speed, we can say the torque of the motor is the torque constant, torque EMF divided by the resistance of the motor, and that's negative, times omega, and plus the torque constant over the resistance times voltage in. Okay, so we've just kind of rearranged and juggled things. Solve for voltage in and solve for torque as a function of omega and the input voltage. So as I increase the input voltage, I increase torque. As I increase speed, I decrease torque, and eventually it'll go to 0 when the back EMF and that applied voltage are equal. Okay. So given all that, we can say that at 0 speed, right, this term is equal to 0, and my torque is just the torque divided by the resistance, KT divided by the resistance times the voltage input. So that's our stall torque at omega equals 0. So given, if we could measure that stall torque and measure that resistance, we could find KT. And that's this point here. And then at no load speed, where the torque of the motor equals 0, okay, if the torque of the motor equals 0, then these two terms are equal, and I get some maximum speed, and the current is equal to 0. So V in over K EMF, because KT cancels out, resistance cancels out, all that stuff. So all that's left is omega V in and K EMF. And most of the time I operate somewhere in between. And as I increase the voltage input, obviously I increase the speed. at no load, I increase the torque at stall torque, and I get operations out to the upper right corner, okay? So there is a set of differential equations. You can see that if I can do some measurements to find some of these constants. The only thing that's really hard to measure is this inductance, and that tends to be small. It may or may not be significant, especially compared to the mechanical inertias. We can apply Newton's laws and the equations to couple the torque to speed and develop a model. And actually, I've got a video somewhere on doing just that, though I used really bad numbers for constants in that video, so ignore those numbers. And that's basically how a DC motor works. So thanks again for watching, and see you later.